Okay, I think that's starting. And there's a chat here. Understood, Jacob. Got it. All right, so those of you on Zoom that always count on Jacob to do all the talking, why don't you guys pick it up? Like, I know last time, I think Niles and Nick and both of you brought it up. So if you could keep that rolling this time, just try to stay awake out there in Zoom land. We only have 2 lectures left. This is one of them. All right. And if you got your book, let's open to, oh my gosh, we're almost done, aren't we? Okay, everything we talk about today is on the final, not the midterm 3. Okay, so we've already finished everything that's on midterm 3. And so maybe I'll do this really quick, just so for the records. Does somebody have a calendar function here?
Yes.
Obviously, we have lab tomorrow. What's next Monday? Is that 11/22?
Yes, sir.
So that means next Wednesday is 11/24. And then, do you agree Thanksgiving is next week?
That's what I got it.
So we have no class. All right, and then,
11/29.
thank you. And then December 1.
Yes.
And then the final is,
Well,
oh wait, what's Thursday? Thursday would be
oh, that's the second.
12:02.
Yeah. Then the final's on the 6th.
Monday, 12:06. So we can kind of, just so we have everything in one spot and so it's on the record. I know I sent you a document, but sometimes it helps just to talk about it. This one, there's the extra credit lecture. If you haven't read that handout last 3 weeks, do you know what I'm talking about when I say that last 3 weeks of class handout? I think I sent it to Canvas. So I'll try and send it again. There was a document in one of them that called last 3 weeks of class or something. In there, I detail all the information, and I can get that to you in lab tomorrow, whatever. But there's an extra credit lecture. And it explains 3 options to get the extra credit. So if you can't come to the lecture Monday at 11 with the NASA people, or Tuesday at 11 with the NASA people, those are the 2 options to attend it live, and it's easy. It's just show up and get 5% on a midterm. It's a 1-hour lecture from somebody from, I think, I want to say UC Riverside, and a NASA scientist. They're going to have solar telescopes out, and Vince Tobin will be there. You can ask him all your magnetic questions. There is an option if you can't make either of those times, and basically you're going to have to watch one of the videos and write some articles, or write a page document, 2 paragraphs or something. So the easiest way to get the credit is just to go to the lecture and sit there and do nothing and try and participate. Check that out. I highly recommend it. If you have questions, talk to me tomorrow in lab. Okay, next Wednesday, your assignment is study at home. All right. You need to do practice tests sometime. That's next week. Obviously, you could do them Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Don't forget, there's no class Thanksgiving. There is a special office hour Sunday, office hours with Brian. I'll say with Bri Y, that's what I call him all the time. Professor Youngblood is what you should call him, I guess. Again, if you need the Zoom link and where the times and this and that, it's basically I have to proctor his final exams for him, and so in exchange, he's doing office hours for you. So that's cool. If you have some last minute questions, you can ask him. He knows what tests you're taking. He knows what problems you're doing. He knows all of it. And he's probably a better physicist than I am, but so he should have no trouble answering your questions. I'm not worried about that at all. All right, he knows physics very well. Monday, this is exam 3, right? Let's put that in red. Exam 3, and that is going to be, we're going to start with some BS. You're going to do some amperes. And then what else? Induced EMF. I'll just say induced EMF, RLs, LCs, LCR with AC. That's a lot of alphabet. But kind of, and didn't we also say filter? That was on there. Remember we ended last time with the filter, like the break and the short crap? I'll just say break short. That's what's on exam 3. All right. And we're going to do lab tomorrow and talk about this piece one more time, just even though you're probably bored with it. Okay, Wednesday, we're going to do EM waves. I'm going to allude to them several times today, but not really go into it. And then we're going to hit it hard. I pre-recorded the lectures for this. So because we only get one shot at this, you may actually want to watch the pre-recorded lecture before this date. So maybe, you know, between Monday and Wednesday, you could watch it, or Thanksgiving week, you could watch it and kind of get a run through and read the book. So actually read and pre-watch video. Just so that class goes smoothly, right? All right. This is makeup lab. As we said earlier when we were talking, I think a couple of students here, you are not required to go to that if you've already turned in every other lab. Now, you are welcome to show up. You could do some exam problems in the corner and just leave me alone if I have to help students that are actually doing the makeup lab. But if I have time, I have no problems helping you if you're there and I'm not helping the makeup students. All right, so, but they come first. And then if you have exam questions, I'll totally help you, or homework or whatever. You're also welcome to come there, look at the lab, play with the equipment and do none of the data, just say, oh, that's neat, and then leave. Or do whatever you want. I would say this, I would not waste your time on it unless you had like a 2 or a 3 for a lab. Now, if you had a 2 or a 3 or a really low score, doing the makeup lab is probably worth the points. But if your lowest lab score is a 6, probably not worth it. You might only raise it 2 points, right? Because I'm a tough grader. So, right, we're doing all that work for an extra 2 points in lab is not worth 3 hours of studying for the final. Everybody clear on that? Unless you absolutely need the makeup, I'd rather have you studying for the final, which is Monday. It's comprehensive. Now, this isn't a perfect review guide, but I'll just mention page 231. Take a look. I'm always wary of giving people review guides because then they'll be like, wait, you gave us something that wasn't on there. So to be clear, there's no guarantees in this review guide, but I think if you study this stuff, like this is what I think about when I'm making a final exam here on page 231. So let's leave it at that. And so of particular note, I mentioned at the very top of there how I handle chapters 32 and 33. And I'll address that in lecture today. But when I do chapters 32 and 33, I usually take some question almost exactly out of the workbook and maybe change one little thing, like a number or an angle or an I hat to a J hat or something like that minor. But I'll do the problems on the rest of the midterm. Sometimes it feels wildly different, right? But on these ones, I try to be super boring. There's going to be a question out of chapter 32 and a question out of chapter 33. Sometimes there's a concept question out of each chapter as well. All right. Cool with that? All right. Zoom, you got all that?
Yes.
Yep.
Any questions from you in Zoom, or is that okay? You're good. If you have questions, let me know. All right. And just so I don't forget to tell you, every year I tend to pick different questions, but I want to kind of point out some ones that I really liked. From 32. I'll have to look at the chapter 33 and we'll do that in the next lecture. I like 32.5 a lot. I like 32.7 through 9 a lot. And to be honest, I can't even remember. Let's just put in 32.1 and 32.4 just in case. Those are lower level, 32.1 and 32.4. I don't think I put those on the final this year, but I can't remember. So I'd rather have you just be aware. Those are the types of things that out of chapter 32 that I might throw on the final. Got it? I would love that if this was a pure academic and we challenged you all the time, I hope you're getting enough of a challenge in this course already that you don't feel like you're getting ripped off here, all right? So normally people don't say I don't challenge them enough, but hopefully you're right. Just be aware, chapter 32, it's probably gonna be something that looks a lot like one of those. Clear? And I don't know what it is. I can't remember, to be honest. Okay, everybody on Zoom got that?
Yep.
Yep. Why don't we just look at chapter 33 while we've got it? Since that way it's all in one spot. Do you agree that would be kind of nice? So from chapter 33, let me see if I can just remember. It won't be perfect. From 33, 1, 2, 6, 8. I'm just going to shout out some that look good to me. 1, 2, 6, 8. And this is on page 226 and 227. I like 9 through 12. 9 through 12. And I think there's one more on the next page. I like them all, but let's just say 14 through 16, just in case. Some of those might be repetitive there, and I don't know which right now. I'm worried that I may have. So to be clear, I'll try and narrow this down if I can next time, but when I look at it, I'm pretty sure it was something one of those, but every year I make new finals and every year I change what I grab. But these look like the ones historically that I stare at a lot. And I'm like, which one of these do I like? Is everybody clear? Those are the questions I like from chapters 32 and 33. So obviously we have a lot of work when we come back on that last day to make sure we get through this. Today's lecture is somewhat fun with a very small amount of physics. You can see there's a lot fewer things we actually need to do. But it's fundamental. Hey, look at those, look at that grapes. It's calming down. Do you see it? It's eventually going to settle down. Another 10 minutes, it'll probably be good. Okay. Ready to do some physics? All right, I'm going to race. Was that time well spent? Are you happy we did that?
Yes.
Okay, I'm going to race. Yeah, snap it. You can walk up here if it helps you. Got it?
Got it.
Okay, and remember, it's also in the YouTube. I wanted to get this up the YouTube, so it's right at the beginning if your picture turns out crappy, okay? Now can I race? All right. Wait on. Okay. And then, all right, so that's kind of better to cover that early. We're gonna start reading on page 215 while I get it ready, while I get the board ready. Page 215, it should say something like electric charge creates electric fields. If one of you thinks of that, maybe you could send me your photo, and then I could tell the other class to make sure I tell them the same crap I sent you. You know what I'm saying? That would be great if you think of it. If not, I understand. I'll just tell them to watch the video from me. I still haven't had time to make that LR transient handout, right? Well. Okay, are we on the right whiteboard? Yes, okay. Okay. So we know this already. This was the first week of class, right? Or maybe it was the second week. We had two main equations, right? Force on a charge was QE. And a lot of times we said DE was equal to K DQ in the R vector over R cubed. Do you remember that? And sometimes we said that DQ was oftentimes equal to one of three things. It was either lambda dx, sigma dA, or rho dV. There were some little tricks that sometimes we used rings and stuff. And if you look, right, we're on page 215. I have a lot more details in there that I'm glossing over right now. But I just wanted to point out a couple of things, right? I'll call this Q, I'll give this a label. The idea is the force on Q naught would be Q naught times the electric field. And the electric field was created by all the other charges around it. Do you remember that? Okay, that's what I mean by the electric charge creates the electric field, all right? And we talked about how the force affects it. We also went on to do Gauss's law, right? The electric flux, which was the integral of E dot dA, and I think we always used a closed integral, I just want to confirm, was equal to Q enclosed. Yes, that's right. So if we wanted to do, you could have electric flux without the closed integral, but I'll put a closed surface electric flux was Q enclosed over epsilon naught, right? So again, charge related to electric field. Cool. This is going to come up again in a minute when we talk about magnetism. Now, all the little details for Gauss's law are listed there on page 215. We had like cylindrical or plates or spherical and shells and conductors. There's a lot of details in there. I just want to move on. Next. The electric current creates a magnetic field. This was the next chapter of things, right? For example, we had the Biot-Savart law, right? This was BS. Biot-Savart. My bad, Jacob. All right. What was the other law that related to current and magnetic fields? Ampere's law, right? That was something like that, right? Let me make sure I'm not screwing this up. Okay, good. We want the closed integral again, right? The idea was if you enclose some current with a surface, this was like the perimeter. So it's a little different than Gauss's law. This was the area of the surface, and this was the perimeter of a loop. Do you recall? So it's a little bit different. But again, we see some parallels here, right? Charge creates E fields, current creates B fields. All right, that's cool. And then where do I want to go next? Here's something new. As far as we know, magnetic monopoles do not exist. They are not mathematically forbidden. They do not violate the laws of physics. Now you might be saying, what the heck is a magnetic monopole? Well, I would say, think of it like, you know how we have north and south poles on a magnet? You know how we have plus and minus charges? But we don't have only a north pole. We don't have only a south pole. So, right, when you have a magnet, it's got a north and a south pole. If you break it in half, you get a new north and a new south, a new north and a new south. You can't just break off the north pole of a magnet and get only a north pole. You can't have a magnetic monopole. What's another way to have, right? Remember, inside of a magnet, there's actually current in the atoms, and that's what gives rise to this. So maybe you're saying, what about a current loop? Let's say we have a current loop here. Now, I know this is kind of hard to see, but I'm trying to draw, it's curling out in the front. In this case, there's a magnetic moment up, right? Now, just to try and make this clear, is everybody okay? I curl my fingers in the direction of current, my thumb points up. Everybody good with that? The magnetic moment is a lot like a bar magnet. This is approximately equivalent to a north and a south. I can tell this because it creates field lines that look like this. Whoops. The idea is the magnetic field lines that it creates look very similar to the magnetic field lines this one creates. So, right, you can't just say a current loop is a magnetic monopole either, because it actually looks like a magnetic dipole. So, again, there's no physics that says it can't exist. No one's ever seen one. If you find one and you get the Nobel Prize, give me $5 and say, okay, cool. You don't have to, but I'd like that. There's an equation that represents this. Magnetic flux for a closed surface. You can see this closed surface information is critical. Equals 0. Sorry, I ran out of room. Now think about this. Compare it to this Gauss's law for a closed surface. You could enclose a plus charge, and then you get a non-zero electric flux. Because we can't enclose a north pole all by itself, right? There's always a north and a south. If I put a surface around this thing, right? There's always the same amount in as out. So this consequence is, if you have a closed surface, you're always going to have the same amount of field lines going in and out. And you could say, well, what if I just cut the magnet in half? That's equivalent to doing this, and you'd still have the same amount in and out. So this equation is supposed to be the same as these words. So far, so good? All right. It's kind of an interesting fact. All right, let's go over to the next board. Any questions from Zoom on this board before I move over? You got it all in front of you, but okay. Come on, there we go. All right, we discovered something else. There's a changing magnetic field will create an electric field. Now I'm going to be super hand wavy here. My claim is that, don't get emotional. Usually, we said this was B. Whoops. Wasn't that usually BA cosine theta for what we're doing in this class? Obviously, it would be the full integral. Now notice, didn't I just say the electric flux was, didn't I just say the magnetic flux was 0 a second ago? Yeah, and you can see now why I'm constantly checking my notes when I want to say closed surface or not. If it's a closed surface, this would be 0. But what if we just have a loop, right? A loop of wire and some magnetic flux through them. In this case, because this is not like an entire box, it's not an entire closed surface like this, right? This, all 4 or all 6 sides of this, right, top, bottom, Well, I guess it's not closed, but whatever. The idea is, if you had a full box or a full sphere, this would be a closed surface. If you just have one surface, you could have magnetic flux. Right? Okay. The main thing out of this, I want you to think of these equations as saying somehow a changing B field creates an electric field. Now you could say, wait a minute, dude, what if the B field's constant and the rod's moving? Okay, you're right. So it's not perfect, but I'm going to lump these together here. And basically, I should probably say something like this. Changing magnetic flux creates an electric field. Or you could argue something like that. And you could say, well, wait, okay, I don't want to talk about it. The fact is, I want you to think of it as somehow changing magnetic field, changing magnetic flux, or something related to that can create an electric field, just like charge. Okay. So let me go over here. Let me go zoom out. Oh, jeez. Sorry. For you on Zoom, right? Charge creates electric field. Changing somehow magnetism, something about it, creates electric field. Two ways. Okay. There's two ways to get an electric field. Now it sure seems like something's missing, doesn't it? When you look at all these equations on the boards here, in particular, I want to make sure the Zoomers can see this too. Right over here, there was a little bit of symmetry. Right? Charge creates E, current creates B. What would be the analogous situation over here on these boards? Exactly. And that's the piece I want to talk about. And just to make them look the same, changing B field creates E, something like this, right? This is my claim. This is where I want to go next. This was a big deal. And it all comes related to old friend, the capacitor. So this is a very confusing problem. Got some parallel plates here. Can you see them online? Parallel plates?
Yes.
Right? And I want you to imagine there's wires connected to this. You can still see it? I'm centered? Yeah, good enough? Close enough? Okay, yeah. So imagine there's wires coming in and out. Now here's a surface I could put in there. Do you agree there's a perimeter here? Yeah. Right? All right, so now let's just keep this in mind. I'm going to draw two capacitor plates here. So what I'm trying to draw is what I showed you there just a second ago. Sorry if this picture is crap. The idea is maybe there's some current flowing this way. And there's some current flowing that way. Am I on the right board? No, I'm not. Let me get there. Sorry about that, Zoomers. Can you see it now? I'm drawing those same capacitor plates up here on the board. Do you agree there's no current up here? You don't have charges jumping the gap from one plate to the other, right? Assuming the voltage is low enough, as long as it's less than, what is it, 3 million volts per meter or something like that. I forget, or maybe it's 300,000. I don't have the number at my fingertips, sorry. So imagine I draw an Amperian loop. According to this, what's I enclosed? How much I is penetrating that loop? Zero, right? There's no actual charges. Okay. But what if I get spicy and do it this way? It's the same loop. Do you agree? But the idea is now I'm going to use this bowl as a surface. Can you kind of visualize that? Can you see that on Zoom? All right, the idea
Yes.
is I use the same loop, but I use this surface. This is supposed to be the bowl. Can you visualize it? What is I enclosed here? I, matey. Doesn't this appear to be a contradiction? That's what Maxwell thought. Maxwell's like, Ampere's law doesn't make sense for a capacitor. We know capacitors exist in the real world. Something's messed up here. Here's my claim. Which one of these do you think? It's a contradiction. They can't both be right. Which one do you think is right? Is there a magnetic? So, right, to be clear, this implies no magnetic field. This implies B equals mu naught I over 2 pi R, right? Which one do you think is right? The purple one is right. So here was the clever thought that Maxwell had. I know there's no current in here, but do you agree if current's flowing this way, which way are minus charges moving? The other way. How about over here? Which way are minus charges moving? So shouldn't this be a negatively charged plate? Can you see that at all, Jess?
Yes.
All right, and shouldn't this one over here be a positively charged plate? What direction is the electric field inside the capacitor plates? Can you see that at all, Jess?
Works.
Okay. Is this capacitor charging or discharging, if you had to guess? It's charging. The current's flowing towards them, right? Do you agree this is more electrons going towards the plate, not electrons leaving? If current was flowing the other way, it'd be discharging, agreed?
Yeah.
So not only do we have an electric field here, I know that dE dt is greater than 0. Do you agree? It's not only do I have an electric field, but it's growing with time. Maybe not that much because it might be close to full, but it's still slowly increasing at this point. All right. Now, hopefully I don't screw this up. What I'd like to do is say this is wrong. And as a result, I would like to erase it and actually work some math out. And I need some space, so I'd like to erase all of this crap. Okay? Okay. Does anybody know any equations for a parallel plate capacitor? Anything you know? Give me anything. Okay, delta V over D equals the electric field. Is it okay if I just do magnitude? And how about I just ignore all the minus signs? You remember, so he's getting that equation from E sub x equals minus dV dx. And what I want to do is just arrange the polarity and stuff so I can ignore the minus signs. Are everybody okay with that? Sweet. Easy crap, easy crap. Well, I'm going to say that delta V equals N, one of my favorite equations. I'm going to keep that in mind. Anything else for capacitors? Anything? You can look at the equation sheet and just start throwing crap at me. The home shopping network applies. Wait a minute, don't we see what delta V equals? Let's shove that in. You're telling me that Q equals NC. Do you agree? All right. Fast Eddie C. Give me that charge. All right. What else? What's C for parallel plates? What's the capacitance of this? What was the formula?
EA over D.
Epsilon naught A over D. Whoa, whoa. Fast Eddie times epsilon naught area over D. What drops? The D's. What's EA? What is EA? Those of you on Zoom can't see it, so I better zap it over there. What's a name for EA? Starts with electric and ends with flux. Man, your guys are good. All right. I'm trying, right? There's a million ways we could describe EA, so I know it's a bad question. I'm trying to give you that hint there, so sorry about that. I just want to point out that the charge is related to epsilon naught times the electric flux. I'm totally hand waving here, but I don't care. So wait a minute, doesn't charge relate to current? How do you get from charge to current? So you're telling me if I take the derivative of this, dq dt is equal to epsilon naught, that's a constant, d phi dt? Doesn't that look vaguely familiar? Right? Check this out. This is called the displacement current. This is on page 217. It's all written up there. We now see the analogous situation. If you're increasing the electric field, aren't you increasing the electric flux? That is mathematically equivalent to a current called the displacement current. Now I should be careful here. Want to make sure whether the epsilon naught, I believe that's in there. Yes. So we can actually go back to Ampere's law and we can change it. Am I on the right board? No, it didn't. Go.
No.
Sorry, I thought I hit the button. It didn't. Sorry about that. This concept is called displacement current. I sent you a video. I think it was an MIT video where they actually made a capacitor big enough that they could put a detector in there and do the measurement live. And you can see it. So if you are curious about how you could actually prove this is true, there's a name for that coil and I forget, and I think it's really cool. Whatever. Isn't that interesting? This resolved the big discrepancy. And so now we don't call this Ampere's law. It's the Ampere-Maxwell law. Cool. As a result, look at the bottom of page 217. There's Gauss's law, the Ampere-Maxwell law, Faraday's law, and Gauss's law for magnetism. Right? You can see on the left side is the integral representation. Right? It's basically the way we've been doing things in class. Most physicists eventually switch over and do things in what's called the differential representation. We don't know vector calculus as a prerequisite for this course. So I can't talk about gradient and curl and divergence, but the math is all there. They are basically the same thing. And you can think of it like this. These certain integrals that have these closed symbols, and where are we here? Let me get out to a full view here. Okay, and I know you can't necessarily see it all here, but the idea is all of the equations that you can see, everything we've done for the whole semester can be summed up with these 4 boxes, and look at that little one down below, that cute little Lorentz force law. Isn't that so cute? That's our whole class this semester. Ohm's law is hidden inside of there. What? You don't see it, whatever. Maybe you've seen those cheesy physics t-shirts that have all these equations on the right and say, let there be light. Have you seen those? You're lucky. Physicists love these. Okay, so Watch, I tell you what, when you go home, go to Amazon and say, "Let there be light" t-shirt, and tell me you don't see that shit. Okay, yeah, let there be light. The reason why do they say let there be light? Let me go one step. Let's get a little crazy here, people. And remember, I've already told you what's on the test, right? So we've covered that. Okay. What is a wave? In your opinion, tell me what you think a wave is. I don't care anything. Energy is it. Now I'm going to go one step further. It's energy going from place A to place B. So it's energy traveling. That's a great definition. What's one type of wave other than light? Any other type of wave? Sound. Okay. How do sound waves work? I disturbed the air. There was a disturbance. How does energy get from me to your ears? Molecules. There's a medium. Okay. There is material. If I clap, I cause air molecules to compress and then they rarefy, right? There's high pressure regions and low pressure regions. And those are going to oscillate as they travel towards your ears. And then when they hit your ears, you're going to get alternating patterns of high pressure pushing your eardrum one way, then low pressure, the eardrum is allowed to expand outwards. And that's correlated to electrical signals that go to your brain. That's a sound wave. Give me another type of wave. How about you drop a pebble in a lake? What type of wave would you say that is? I would call it a water wave. What is the disturbance? You drop the rock. 1/2 GT squared. What is the medium? Water. Water. What's another type of wave that matters around San Andreas Fault? Earthquakes are waves. The disturbance, a plate slips. Right? Tsunamis, a plate slips under water, or there's many sources, but you can have a megathrust, a plate comes on, and you can, yeah, there's all kinds of neat stuff. If you're really into that, talk to me after class and see if we can get you up at Stanford, okay? You can do an internship at Stanford if you're really into tsunami waves. We have a connection, right? Now, in an earthquake wave, the disturbance is the fault slip. What is the medium? The Earth, the planet. How about you're playing bass? String waves. What is the medium? The string. The string, right? So, right, if you pluck the string, it's going to vibrate. The disturbance is heavy bass. Okay. We need that fat bass tone. All right. Now, all of these, this is the point. All of these waves, those are the main ones we study in physics 1, 2, and 3. They all involve a medium. And I don't mean, I'm talking about some substance through which the wave travels. Let's go to outer space. How much stuff is there in outer space? All of it? Okay. Think about this box that you can see in front of you here, right? I'll try and we'll go down here. Whoops. The back of your head is in there. All right, so whatever. You're in it to win. So I'm looking at this thing right here, right? This desk. How big is this desk? About? Isn't it about 1 meter cubed if I just look at this corner? If you just kind of eyeball it, it's about 1 meter what? 1 molecule per meter cubed in outer space, approximately. Okay. Oh shit. I don't want to touch those grapes. I may have screwed this up. That's all right. So here's the deal. There's not much in space. There's no medium. How are we alive? We need to stay warm. Slapping the base is not going to keep us warm. Well, unless it's really vigorous baseline. But it's these two equations. There's an electron somewhere in the sun wiggling. When it wiggles, doesn't that create a changing electric field? Doesn't it also act like a small bit of changing current? So doesn't it also create a changing magnetic field? And the interaction of the changing electric and magnetic fields, in a sense, replaces the need for a medium. Because there's a changing electric field, right? The idea is I'm right here at this point in space, and there's a changing electric field and magnetic field here, right? That's going to cause a changing electric field and magnetic field here, and here, and here, and here. And that's what allows these waves to propagate through empty space without a medium. That's why you see these stupid equations with a shirt that says, let there be light. This is what allows light to transfer from the sun to the earth. Isn't that cool? This is a big deal. It's arguably one of the most important set of equations in existence. That's why you always hear about Maxwell's equations and this stupid phrase, let there be light. Okay? All right. We are going to discuss EM waves more, electromagnetic waves, and I'll try to give you more knowledge about that soon. But the fact is, this is a huge, beautiful chunk of physics. I know I don't normally do lectures like this. It's because then you wouldn't know how to do anything, right? This is the most fun stuff, but sometimes you actually have to know how to do something as well. And that's why I normally teach the way I do, is I want you to be good at doing something, anything. All right, any questions about this right now? Anything you want?
Dr. Stead, we're still looking at the desk.
Good, that's a good desk. You guys can wave to them back there, right? There we go. All right, sorry about that. Fortunately, we didn't need anything there, but yeah, whatever. We'll just go back out to this. So again, the idea is all these equations are beautiful. They relate to electromagnetic waves. We're going to discuss that a little bit more. And those of you that take Physics 162, you're going to learn a lot more about waves and see these equations and equations similar to them in that class. Those of you that already had 162 probably know a lot of this stuff already. All right. Good, good. Other questions? Anything from Zoom as well? Or are you doing all right? All right. Where do I want to go next? All right. Fortunately, we got time to let this restabilize. I'm going to try and bring up a simulation. Okay, and I'm going to go on to page 218, the Earth's magnetic field. Okay. I feel like these are important things that I have to talk about because they're just so fundamental to life on Earth, and yet they're not on the test. Right? You know what's on the test. I told you already. All right. Oh man, that's Pink Floyd-esque. All right, and I want to go to PHET. Okay. While that's going, I think I can do a screen share. Oops, I'm in Zoom meeting. So while that's loading up, I'll mention a few topics about this. So we're talking about the Earth's magnetic field. The Earth's geographic north pole is the approximate location of a magnetic south pole. This is why the north pole of a compass, it's gonna, there it goes. Now we got this up. The idea here is I'm trying to emphasize the following. Look at the North Pole. There's a South Pole at the Earth's North Pole, and there's a North Pole at the Earth's South Pole. And this can reverse, right? And throughout history, it has reversed. If you want to, you could read about pole reversals. And maybe you remember the magnetic bottle simulation. You guys remember that? The Van Allen belts? That relates to this. I'll mention this really quickly here. Let me get this over here. Is it this one? You guys could make this yourself. Oh, and let me clear those annotations. Sorry. Right? Okay, except, okay, come on now. Cookies. All right, so this is what the Earth's magnetic field, you could imagine it looking a little bit like this. And so you can see the arrows here. It's going to be stronger at the North and the South Pole. If I could go back to this one, right? You could imagine it kind of looks like a giant solenoid, right? Isn't that what a bar magnet looks like? You could imagine this as a giant solenoid as well, right? Where you'd have this current going around like this. Which way would the current be flowing in these rings? Would it be going this way or would it be going that way? Top or bottom? Bottom. Because wouldn't that make it like a North Pole grab that solenoid? Like, yeah. Does everybody kind of visualize? That would be pretty similar because the magnetic field lines would be coming out. Let's see, they would be coming in here and out here. So obviously there's not a giant bar magnet inside the Earth. There's not a giant solenoid inside. But what is inside the Earth that causes this magnetic field? We'll get to that in just a second. Let's go back to here. All right, because of that magnetic field, that kind of looks like this. You can visualize that magnetic field. Do you agree? Out of the bottom and into the top. The idea is charged particles will bounce back and forth like they did in the magnetic mirror. Do you remember those? You guys got that okay? And so these are called the Van Allen belts. We get these belts of ions that are trapped, and instead of frying our circuits, they get trapped by there. If the pole reverses, do you agree at some point there's no magnetic field? Right? What if the, right? If to go from north on top, or sorry, to go from, if we want the pole to reverse, where we want a south pole on the bottom, right? Maybe you don't realize this. There's going to be a point in time where the pole, the magnetic field could be zero. And that could happen for 5 minutes or 5,000 years. And that could be a problem. Now, if you're worried about the whole world dying, you could read about this, and I think they've shown that the radiation bombardment shouldn't be enough to kill all life on Earth. So I think we're good there. But if you want to learn more, you can study more. Okay, read about the Van Allen belts and pole reversals if this is a topic that interests you. Not on the test. All right. Where did I want? Yeah, right. What was the point of this? Oh, there was one other thing that I wanted to talk about the Earth. This is cool stuff, right? Oh, let's go to our friend Wikipedia, right? So inside the core, you could imagine there's a lot of hot thermal material that can flow around and cause ions to spin around and create these magnetic fields. And then if you read this stuff down here, what keeps these currents going, right? Why don't they die out? Because there should be a lot of resistance. Well, there's Coriolis, there's circulating, I don't know. There's all kinds of stuff that I don't understand. This is the accepted theory right now, but it's still a theory. I think at the time of writing this, it appears this is likely correct. So when I wrote this workbook page, I don't know if this has been, I think this is the most popular theory to explain why these magnetic fields exist. And there's all kinds of interesting stuff. If you want to read about this, that's cool. Hey, no magnetic monopoles. All right. Great. Is everybody okay with that? That's the Earth's magnetic field. Any questions on that? I hope not, because I don't know anything. Now, I want to talk about fruit. So, take a look at page 219 while I get the next thing ready, okay? It's pretty interesting stuff. I'm basically trying to give you the highlights of things that you might care about. These are interesting topics, but unfortunately not the subject of this course. Grapes, however, are. All right. It's fogging up.
Get out of the way.
It's like you get Christian's toque in there. I call a stocking cap a toque. All right, so that's fine. That keeps it real. I like to have, there's an old physics joke I like to use. Well, it's not that good. Keep it real. Plus a small imaginary part. Do it with rotation. When you get to field theory, you can laugh at that. All right. There's an old trick you can do if you have trouble doing an integral. You can add a small complex number because then you go around the zeros and the poles. That's another old joke. What do you get when you do a contour integral around Copernicus's grave? The residue of a pole. It's a physics joke. That's a mathematical term. All right. These grapes are turning. I claim I can stop them. Hopefully. I'm going to make it go the wrong way. But how do we know it wasn't just the string making it untwist? I could stop it again.
No way.
And then I can restart it again. Do you agree these grapes are being repelled by this pole of the magnet? How do you know I didn't just put a magnet in there? I'll use the other pole. This is a really big magnet. I have to be careful. Do you agree it appears I can make it start and stop in this rotation? Over and over and over again? One more should do it, I think. And it doesn't matter which pole I use. Do it this way this time, right? Are you satisfied that I can make these grapes be repelled by a magnet? Now, obviously, do you agree this is an extremely weak repulsion? I have to hang this by a string, let it sit there for like 30 minutes so that it's barely moving. And even then, I have to like sit there very carefully and not move too fast, because if I just move my hand really fast, I probably get more force this way, right?
Yeah.
So this is very, very weak. But these grapes are repelled. This is an example of diamagnetism. And I ask you to think in your life, when's the last time you saw this? I'm going to assume never. We don't usually see magnets repelling non-magnetic materials. And that's, I guess, at the heart of this. Grapes are magnetic. Everything in the world is magnetic at some level. And this basic type of magnetism that all objects, all atoms, everything exhibit is called diamagnetism. Okay? Take a look at that page right now. I'm going to erase the board. We're looking at page 219. Okay? Give me a second. So diamagnetism has some weird properties. Everything in the universe is diamagnetic. Everything in the universe is repelled by a magnet. However, there are other types of magnetism, paramagnetism and ferromagnetism. Those two types of magnetism are stronger than diamagnetism and are sometimes also present. If paramagnetism or ferromagnetism is present in a material, you're never going to see the diamagnetic properties of that material. Okay? Paramagnetism dwarfs diamagnetism, which is dwarfed even further by ferromagnetism. Most of the magnets that you know, like this giant magnet right here, see it's ginormous. Okay, that's a ginormous magnet. That is a ferromagnetic material. Now, I forgot my bottle of liquid oxygen, which is a paramagnetic material. Have you ever seen this? Liquid oxygen is paramagnetic. So, okay, let's put some summaries here. All materials are diamagnetic. If para beats dia. If ferromagnetism this is how I like to think of it. Ferromagnetism is the strongest type of magnetism. Ferromagnetism uses things like your rare earth, neodymium, maybe you know that. All these notes are written there for you, okay? Neodymium, iron, ferro, iron. Okay, alnico is another common one. What is that? Aluminum, nickel, cobalt. Interestingly enough, I think aluminum by itself is diamagnetic, because if you try to use aluminum as a transformer core, it's worse than air. If you don't believe me, wrap some coils around it, stick an aluminum rod in it, and check the power transfer rate. It's actually worse when you put aluminum in than when you use air. So I don't know. Chemists are probably better at this stuff than I am, but I just wanted to let you know there are 3 types of magnetism. Now, there's something else. Dia and para go away when magnet removed. But I'll say external. So essentially, diamagnetic materials and paramagnetic materials, you don't notice their properties until you bring a magnet close. This is why you aren't worried about fruit being magnetic usually, right? Frogs are magnetic. You can levitate a frog with diamagnetism, right? They've done this. One could argue whether it's humane. I have no clue. That's not my expertise. All right. What is weird is that after a magnet is removed, ferromagnetism can persist. And you have probably seen this. Have you ever magnetized a bunch of paper clips and then pulled the paper clips off the magnet and they're still a tiny bit magnetic? What my parents used to do to me was they'd say, here's a nail, go sit in the garage and take the nail and rub the magnet over the nail over and over. That's what I plan to do for the rest of the lecture. That's a joke. The idea is, I don't know if you can see this on Zoom, but I've just taken a piece of iron here and I'm running a magnet over and over and over again. If you do this long enough, some of the magnetism actually persists. What's happening inside of here, there are things called magnetic domains. And you could think of that as small regions in the material. I gotta be careful with this magnet. I seriously gotta be careful. I'll just draw a picture of it. Right? Ferromagnetism. Maybe you have a bar of iron. Inside it, there might be regions that we could call domains, like this. And this relates to the spins of the atoms, etc. We could talk about orbital and spin and all this stuff, but for right now, let's just say there's some magnetic moments. And what happens is small regions of the iron will group up. And when you have iron that's just been sitting there for a long time, maybe it's got domains that are kind of randomly oriented, right? Like this. And the idea is, if you take a magnet and run it over here, gradually what's happening is you're helping to align the magnetic moments approximately the same way. Maybe not perfectly, but notice on average, there's some tendency of these magnetic moments to go that way, which would make this a north pole and this a south pole, and the magnetic field would be created. And this can persist even after the other magnet is removed. This is fundamentally different than these 2 types of magnetism. Okay with that? All right. There's another weird property of ferromagnetic materials. other than this. All right, let's make sure I don't screw this one up. Give me a second, Zoomers. Old friend, the hot wire. Oh, many fruit flakes. Watermelon. Great. Remember that Christopher Walken for Skittles commercial on Saturday Night Live from like 200 years ago? Watermelon. Great. Okay. Hopefully that's not plugged, turned on. Good. Great. Got a lot of stuff going on here. All right, let me get this on Zoom real quick. Sorry about that. Okay, now on Zoom, you may not be able to see this very well unless I put something. Maybe, hey Christy, can you stand up and help me out? Can you just help me move this up to the table so they can see better? Hand me the power supply and the wire. Big magnet, right? Put this, careful, it's gonna grab that tool. Okay, just put it somewhere on there and just get the hell out of the way. All right. I'm gonna raise this up. Hey, there, you can see the wire now, right here, right? Zoomers. All right. Gonna heat
Yes.
this. Okay, I'm gonna turn this on. This is iron. Generally speaking, what happens to an iron wire when you run current through it? It heats up. What should happen to the resistivity of this metal when you heat it? Goes up. Semiconductors goes down, metals go up. And it goes down is the one I almost always put on the test to see if people listen. So it's good that you remembered that, right? All right. So I'm going to turn this on. There's going to be a large voltage. What do we expect to happen to the current? What happens to it as it runs current? Yes, actually, it will right. Do you agree there's some inductance here? So technically speaking, it'll start at 0, then ramp up, and then it's going to be so hot, it's going to start dropping. Yeah, okay. We don't think of this as having an RL transient, but yes, it does. Watch the current. Can you see this on Zoom now? 40?
Yes.
30, 28? Do you agree it's rapidly heating? Okay. Can you see the dial settings in all Zoom? Can you see the settings?
Yeah, you can see the number display.
Okay, got it. All right. Now, do you agree this is magnetic? I got a little magnet here. This is what's different. I'm going to heat this up. So I'm turning up the voltage so I can get more current and putting my face really close to an extremely hot wire. Is that heating up? Can you see that on Zoom? Oh, I better be careful here. Look. Oh, geez.
That's white.
Do you agree it's not magnetic anymore? Oh, it's a little bit. I gotta be careful because if I go too hot, it's gonna burn. Jeez. Okay. Oh my God. Okay. Well, whoops. All right. Well, I might need a new piece of iron. Yeah, it's gonna be hot. Where's Nick? I want to throw it to him. Okay, I better be careful. These are live, right? This is a lot of current. So I got to be careful. If it gets too hot, the property that I'm trying to show you is called the Curie temperature. If you heat it up beyond a certain point, we've been abusing this wire all day, and it may have gotten to the point where I just can't use that sample anymore. Let's turn this way down so I don't screw it up again. Let's just do this. Okay, it's heating up, right? I'm probably gonna burn the wood that way. I should probably put it on the inside. That's what I was trying to avoid here. Enough. It gets hot. Yeah, that was really, really painfully hot. Okay, let's try this again. Jeez. Can you still see it on Zoom? I think it was somewhere right
Yes.
around 24 amps. So I got this to be stable, right? It's still magnetic, right? Still magnetic, agreed? It's usually if I get it to stabilize around 24. Okay, it's getting red hot. Do you agree it's not magnetic anymore? You see that? It's not snapping. Listen. Well, there might be a little bit. That's really hot. It's not really magnetic anymore. Okay. Oh man, there's a tiny bit. All right. So probably what's happening is when I touch this to there, what happens? I have a large piece of metal. It can probably cool it off just enough to make it magnetic again. Right? But this is not magnetic as when I turn it off. If it cools off, give it a minute. Even though you don't see the heat, there's still some on the inside. It takes time. But do you agree it's clearly magnetic when it's cold, and beyond a certain temperature, we see a significant change in the magnetic properties. This is called the Curie temperature. All right. So in this case, look somewhere in this handout on page 219. Right. This is another weird property of ferromagnetism. Sorry it took so long to get that right. All right. So the other thing that's really weird about ferromagnetism is beyond, I'll call it T subscript C, the Curie temperature, no ferromagnetism. That is weird. That is very different. Now, if you read carefully in the handout, I think paramagnetism decreases, but I'm not sure if it goes away exactly. And let's be clear here, this is not my expertise. Vince Tobin knows a lot more about magnetism than I do. If you want to meet Vince and look through the solar telescopes on Monday at 11 a.m. in M205, both those lectures are in M205, Monday and Tuesday. Right, they're going to have somebody from NASA there with a 50 millimeter scope, and Vince is bringing out an 80 millimeter scope, and they're going to look at sunspots and do weird stuff. And right, when those two astronomers get together, I bet there's going to be some special stuff going on. So if you guys want to check that out, cool. Enough salesmanship on that. There's this weird thing that happens where you go past a certain temperature, magnetism changes. Do you know anything else that behaves like this, where when you go past a certain temperature, something dramatic changes in a substance? What's that?
Chemistry, basically. So like a bunch of like material science.
I'm thinking water. Does water have some special temperature where it dramatically changes? Yeah, 0 Celsius and 100 degrees Celsius. Think about it. What is the general name for what happens when water changes from water to steam, or ice to water, or vice versa? Phase change. This is another type of phase change. You're going from a magnetic state to a non-magnetic state. The physics behind all of this is far beyond us at this time, but if you're curious, 4 years from now, when you hear about a thing called the renormalization group, you could say you heard it here first, and that's worth nothing. All right, so anyways, this is one of the general classes of things called phase transitions. And the physics behind that is very complicated. It's something you usually learn about later. It's really cool. There's these integrals that should be infinitely large that become -1/12 for some reason. It's really wild. All right, good on that? Should we take a break? That's types of magnetism. There may have been some stuff I skipped over. Just to be clear, read the book on this, and that's great. Let's take a quick break. Really cool stuff. Lot to learn. But you know what's on the test, right? Those questions I told you. So there you go. Yeah, I guess my philosophy is I want you to experience this and see it, and then I still want you to be able to pass the test because this is infinitely large amount of material. Zoomers, do you have any questions while these people are going on break here? All right, let's take that break. simulation. Okay. Erase some stuff. Here's a fun puzzle for you. So you can see this. This is a thing. I think I did this once and I can't remember now. I was trying to think of a way. I can't remember now, where you could have the magnet and have this be basically something you could just leave sitting there. And then when it gets too hot, it would disconnect from the magnet and then you would cause the current to stop running so that it cools off. And then it then readheres to the magnet, which starts current running, and then you just have it go on and off and on and off, right? And you can do this because these neodymium magnets can conduct, right? So if you can think of a clever way to do that, I thought it would be fun to build this and then let kids stare at it and wonder what's going on.
Couldn't you just put a glass tube over the, like a thick glass tube over the wire? Yep, and then attach it, and then it could just, well, it has to be a decent diameter, and then it could just fall off, and then back on, once it cools off again. But it
well,
wouldn't turn the current off, so that's the thing.
yeah. I don't know. And obviously there's lots of ways you could do this with transistors and other than, yeah, I was trying to think of the simplest possible way to basically, when it gets too hot, it disassociates. So you'd have to have a voltage that then connects to some other resistor
So you
somewhere.
just watch it and just turn it off at certain points. and stuff.
Yeah, well, that's not this. I thought it'd be cool if it could just be constantly
Oh, keep
connected.
going back and forth.
Yeah, and then I wouldn't have to do anything. And then I could put it out at a science show and the kids would be like, what is going on? Then you talk about all this stuff and they ignore it completely. But it'd still be cool because I think it'd be cool. Anyways, if you think of a cool arrangement, let me know. Transistor is the way to do it, I'm sure. Transistor is basically, do you guys know what a transistor is? All right, good thing we got a chemist here. We'll challenge you here because I don't know much. So let's see other people. So I know this may seem strange, but it got the Nobel Prize, so it's probably worth talking about. Let's say you have a chunk of silicon. Okay. And then let's say you have some boron. What's phosphorus? Help me out. Generally speaking, how does boron ionize? Positive or negative? Do you remember?
That one should be right there, so that one. Oh, it's weird.
Which way is it going to go? How about phosphorus? Which way does phosphorus go?
Oh, so that one's good. That's the negative charge on it.
This is going to be negative, so take a guess what boron does. Hey, sounds good to me. So boron, I think, can go 3 positive and go all the way over.
Yep.
All right. Anyways, but so you could put a piece of material in here, and the idea is you could dump some boron right here and right here, and then these regions are called p-doped. They're positively doped.
Oh, okay.
You've doped them with positive ions. This would be n-doped negatively. So you put the phosphorus in there, right? Now, when you do this piece of silicon is normally a semiconductor. You're changing the conductivity dramatically when you do this. And then what you can do is you could put an electrode right here and wires right here and here. And the idea is you could apply an electric field here and create a field effect transistor, effect. You've maybe heard of MOSFET power, but whatever, metal oxide semiconductor FET, field effect transistor. I hope I'm not screwing up the words because that was not what I was planning, but right, the idea is depending on whether you make this positive or negative, right, you might get a region in here where the conductivity is affected because you might change the electric field may have some effect on these end dopings, on this end doping inside of there. And the idea is, depending on the voltage you apply to this wire, current could either pass or not pass. You've made an electronic switch. That's huge. And do you see why I brought it up now?
Yeah.
You could do something like this where the magnet on this wire would maybe connect to this, and then that would turn on or off the circuit. So it's like perfect. It's screaming out for a transistor. Now, to be clear, you may be asking, is there an NPN? You bet. You can have PNP and NPN. Furthermore, you may be wondering what a diode is. So there's different types of diodes. So basically, doping semiconductors like this, which is far beyond the scope of this course, can create all kinds of new digital electronics. Kind of a big deal. Okay, is everybody cool with that? I'd like to erase this and get on with what matters. All right. How are we doing on time? We're good. Kind of interesting. If you're into that, take a semiconductor device physics class. And it gets wild. It's pretty interesting. Enough said. Now, okay. It'd be cool if you all pass the final. Agreed? Let's talk about some old school stuff. Let's just call this theta for right now. There's some angle in between them, right? Okay, this is an external mag field. You all know that. This is coming from some magnet somewhere. What was mu again? What did mu mean? Magnetic moment. Now, generally speaking, when we talked about magnetic moments, where did they come from? What had a magnetic moment? When did we talk about this in class? Coils have a magnetic moment. Do you remember that? And we said that, oh, if you have a current loop, so you can even have a single current loop. So you could imagine this magnetic moment is up. Which way is current flowing? Would it be like this, or would it be like that? The first or the second? The first one, right? So do you agree this is sort of like a current running this way? What would be the analogous situation if you had an electron in orbit? Now, obviously, they're not little hard spheres. Which way would this electron be moving at this instant? The opposite way. Do you agree? Now, obviously, electrons are not little balls that carry charge spinning around. There's some quantum mechanical thing that you've learned about in chemistry or will learn about in Physics 162. However, for this demonstration, I want you to think about this. Do you agree electrons in orbit have a magnetic moment? And do you agree that an electron or a proton, let's go to a proton right now. Let's say you have a charge and you spin it. So let's say this is orbiting, not orbiting, but spinning. If it was spinning around, wouldn't that be charge going in a circle? I tell you what, I want to make it spin the other way. If this charge was spinning that way, isn't that a lot like this picture? Because it's a plus charge. So even though charges are not little billiard balls that are spinning, you could think of it approximately like that. This would create a magnetic moment up, right? So what we see here is that orbiting electrons and spinning nucleons and spinning electrons will have magnetic moments. That means they have magnetic properties. Now, if you recall, a magnetic moment up, I hope I'm on the right Zoom screen. That would have really stunk, huh? Do you agree this is not exactly the same as, but kind of like a bar magnet with a north-south, or it's equivalent to a current loop? All of these are equivalent, sort of, right? They all have a magnetic field that goes up. Okay? So, in this picture, even though this seems super abstract, where you have an external magnetic field and a magnetic moment, I want you to think about this as possibly representing electrons, or maybe a bar magnet, or maybe a loop, or some sort of current, or something like that. So it's quite possible, you could see something like this on your test, where I give you a magnetic moment and an external magnetic field. Could we get the energy associated with this? Do you have your exam equation sheet? Please tell me it's on there so I don't have to make any changes. Let's say I want the energy associated with this configuration. Do you see it on there somewhere? What letter is energy? U. What's the formula? Let me do it this way. Yes. Did I not have the vector on there? Okay, good. Yeah, yeah. Sorry about that. Negative mu dot B. What about torque? What's the symbol for torque? Tau. What was that, if you had to guess? Not dot. Does it have a minus? No. Did you find it on your exam equation sheet? Okay. You gonna remember this on final exam day? Hit! Hit! You gonna remember all this?
Yes.
Good, good, good. I like that. Sometimes you just gotta telegraph it for the final. All right? Whatever. I think these are important enough to tell you this is coming, right? I told the other class it's coming too, right? You got to know these two equations, in my opinion, because this helps us understand how matter interacts with a magnetic field. Now, we don't know everything about it, but I'm going to try and give you a little hint on this. First off, what direction is the torque here? Give me the direction of the torque.
Into or out of the page?
Which one? When you're doing torque, what's your right-hand rule? Second vector goes to first? Or is it first goes to second?
It's definitely.
First vector goes to second. Which is it, Jacob?
Into the page.
Into. Okay, do you agree? I'm going to write it like this. Do you know what I mean when I say torque hat? Direction of torque. Everybody good with that? All right. How would I get the magnetic energy? What's the equation I might use? What angle does this look? Well, whatever. Just give me the general equation here. How does this relate to the angle?
Mu B cosine theta.
Nope. Look closely. Everything you said was part of it. What's missing?
Oh, crap, the negative.
And I'm going to try and explain that negative and its meaning in a minute, okay? But that's the most common way you're going to screw this up. Do you agree? You forget the minus sign. So now you screwed it up. If you wanted to get the torque, what would it be? What's the analogous? Let's say I wanted to get the torque magnitude. What would it be?
Mu B sine theta.
Yes. Some basic cross product and sines and cosines and stuff like that. Okay, got it. Does everybody agree we could calculate these magnitudes? And all right. All right, so now I want to talk about a specific example here. We're going to make it. Maybe get out early for real for once. I doubt it. There we go. Okay. Let's do a quick example. Let's say our external field is up. Okay. Let's say our magnetic moment is downwards. What's the angle between them?
180.
180, right? Now, do you think this is a high energy state or a low energy state? I'm not sure. Let's compare it to this other state before we get crazy. Because it helps to have something to compare to. Sorry about that. Let's say the magnetic moment is up. Which one of these do you think has more energy? When they are aligned or when they are anti-aligned? Let's do the math. Okay, let's say this is U equals minus mu. Oh, let's get crazy here. The caps are off. Okay. What's cosine of 180?
-1.
Neg 1. What's the U?
Mu B.
UB. You agree it's mu? And do you care if I drop the B external? No, I'm not gonna. It's UB. Let's do this other one. Am I on the right board, Zoom? Yes, okay. What's the angle between these two puppies?
Are they supposed to be right on top of each other? Okay.
Yeah, they're right on top of each other, right? So the angle's 0, agree? Pointing the same way, angle 0, pointing the opposite way. So we call this aligned and anti-aligned, or this could be parallel and this would be anti-parallel. All right. Well, what's cosine of 0? 1. So what's the energy in this state? Negative mu B, agreed? Which one is higher energy? This is more energy. It's pointed the wrong way, right? When you squish a spring, it has the potential to move. It's got a lot of potential energy. When you point a magnet the wrong way, it wants to flip. It's got a lot of potential to flip. It's got a lot of potential energy. When they're pointing the same way, they don't want to flip. So I'm going to call this the high energy state. And this would be the low energy state. Okay? When they're anti-aligned, high energy. Aligned, low energy. So far, so good? 3 to 4. What do you need to make it flip from the low energy state to the high energy state? If you want to make it flip, do you agree you need energy? Yeah. How much energy do you need to make it flip? Yes. The change in energy would have to be 2 mu b. Agreed? Or not 2 mu b? That is the question. So bad. Everybody okay with that? The energy required to flip is actually twice the energy in the high or the low state, so to speak. All right. Now, what are some types of energy that can, remember now, what do these mu's represent? This could represent, say, a proton, right? And it would represent the spin of that proton. What are some ways you could give a proton enough energy to flip? What's one type of energy that can be used to flip a proton? What's that? Kind of, yeah, okay. I don't like that one, but it relates to, yeah. So the short answer would be yes, but I kind of was hoping to phrase it in a different way. What's a type of energy we've seen today in class that was kind of dangerous? Okay. I was thinking of this wire that got really, really hot. Temperature, thermal energy, right? So imagine this is inside a block of Swiss cheese in the microwave and you're microwaving it. Couldn't the thermal energy somehow cause, and that relates to the kinetic energy of other molecules around it. So we talk about the kinetic energy is something like 3/2 NK Boltzmann T in physics 162, those of you that know this. So the idea is, right, temperature relates to kinetic energy. So this is something like, I don't know, number of degrees of freedom, and it's complicated, but the kinetic energy relates to temperature. So basically, if you have a piece of metal and it's warm, or your body is warm, right, it's above absolute zero, there's kinetic energy in the molecules that are associated with that temperature. So I would say you could heat it up and the thermal energy or the kinetic energy from molecules could agitate it. You could get bumped into, right? And that's where that's coming from, thermal energy. Is that cool?
Yeah.
So it's exactly what you were saying, but I wanted to say thermal somehow. Okay, what's another type of energy? I'm thinking of a bad physics t-shirt with 4 differential equations on it. I said, let there be light energy. Wow, that's really good. You could send in a photon, couldn't you? Right? Now, maybe you know this. You could send in a photon or a radio wave. Now, I know you might not think of radios as being light waves, but they're both electromagnetic waves. Gosh, if only we had time to talk about that. Oh, that's our next lecture. For now, I want to point out there is an equation. Who knows the equation for the energy associated with a photon? By the way, the symbol fish swimming down, or gamma, this is a gamma symbol. That's the symbol we use to name something a photon. So this means energy of a photon, and we'll bring this back up next time. Does anybody know the equation for energy of a photon? I'm looking at 162 people. You guys remember it all? All right. How about chemistry people? These are 2 ways we see it. It's proportional to the frequency, or it's HC. So to be clear, H, does anybody know what H is? Starts with a P, ends with the word constant.
Planck's.
Planck's constant, yes. Very good. You know the number for it? 6.626 times 10 to the minus 34 joule seconds, I believe. It's on your equation sheet.
Yes.
Okay. It's some number. What was it? 6.6, 10 to the minus 34? Is that right?
Yes, we do.
Joule seconds. That's a lot of action. I believe that's the physical unit of action. Action is a physical term. Whatever. Okay, maybe you've heard of the path or the principle of least action. Okay. C is another constant. Does anybody happen to know what C means?
Speed of light.
Speed of light.
Speed of light. Is it possible that the speed of light could be 1 mile per hour? Yeah. So this is not just the speed of light. We should say it's the speed of light in a vacuum. Fortunately, in this class, we'll only deal with that. I'm running out of room. For this class, we're just going to call it 3.00 times 10 to the 8th meters per second. So this is the speed of light in a vacuum. Okay. Does everybody know what the symbol lambda means? I'm running out of room here. Wavelength, have you heard that term before? If not, we're using it tomorrow in class, so you better know it. F is frequency, we know that, right? Okay. What's the point out of all this? We're going to discuss this more next time, but the idea here is it possible that the energy of your photon could match this amount of energy? Is it possible then to use a photon of a particular frequency or a particular radio frequency wave could be sent into an atom and cause its spin to flip? That's cool. Now let's go to our simulation. There's an old chemistry joke, if you need to remember this. Maybe you know this as the Greek letter nu. That's what you
it
took,
is. Okay.
right?
Yeah.
What's new, guys? E over H. Okay. You can use that your entire life and it never gets old. What's new? E over H. C over lambda. Okay. Hold on. Let's get screen-tastic here. Did I turn it on? Did I forget the screen? I forgot the screen. I was too excited about my joke. Open sine theta. There it is. Is it coming on?
It is.
All right. Woo! Great. I'm going to turn the magnetic field off. Now, can you see this at all? Can I make it bigger? I don't think I can. This is like old school. They barely run this simulation anymore. So there's a bunch of Zoom crap there. All right, we can deal with this. All right, so I want to draw your attention to the following. Right now, B external equals 0. Agreed? Look right here. There's no external field. When there's no external field, do you see a high energy level and a low energy level? No. Right? Remember, the change in energy between the two levels is proportional to 2 mu B. If B equals 0, what's the energy change between the levels? And if there's no energy difference, there's no difference. There's no, okay. So what I'm going to do now is I want you to watch this side of the screen here that I'm circling, the energy diagram. All right, and I'm going to turn up the Tesla. Wait, oh my gosh, I got too many. Okay. Oh my gosh, sorry, I'm starting to get, my brain's starting to lock down. I got too much Zoom. I'm just going to crank this up. Do you see the energy splitting? We see an energy level splitting. You see that? So in this case, now there's a high energy state and a low energy state. Which one has more? And to be clear, what are we looking at here? We're looking at the nuclear spins. So remember I said mu can represent all kinds of things. In this case, mu is representing like a spinning proton, which isn't really spinning, but it's kind of like that. So these are spinning protons. Are all of them in the low energy state? No. Why are some of them in the high energy state? What gives some of them enough energy to flip up to the high energy state? Thermal energy, right? This is not at zero temperature. There's always some thermal energy. So some of these nuclei have just enough thermal energy to be upside down, to be opposite the magnetic field, to be in the anti-aligned state. Some of these have enough thermal energy to be in the high energy state. That's a dense sentence. Did you get that? Feeling okay? All right. Now I could send in some radio waves. So I'm looking right down here. This and this are my two radio controls. I can send in radio waves. That's basically like sending in light. Okay, radio waves and light are both EM waves. Right now it's off, but let's do this. Let's send in some. I'm going to jack up the frequency to 85, and I'm going to turn up the power here. Now I want you to pay attention over here. See this little squiggly line? I'm circling it right now. You see that? That's the energy of the photon. Does the energy of the photon equal 2 delta U right now? Does it equal the energy difference between the two states? It's more. It's more than 2 mu B. I may have misspoken there. I apologize. Okay. So I want you to kind of keep an eye on those things right there. And let me undo that last one. So where the arrows are, right? Now, what if I go to too low a frequency? Nothing's happening. But what if I match this exactly? I think it's right at 60. Whoops. Can I just make this exactly 60? It's pretty laggy here. If I make this exactly 60, do you see this is causing these nucleons to go to the high energy state? You see that? Now, do you notice that every once in a while, right now it's all in the high energy state, but one of them is going to fall down. Do you see that? Every once in a while, some of them fall down. When they fall down, they emit photons. Let's view this as photons. I'm sending in a bunch of photons. That's what radio waves are. They're just like light. They have photons. When I send them in, if one of those photons happens to hit a nucleon in the low energy state, it flips it. So far, so good? Now, to be clear, when they relax, by relax, I mean when they drop down to the low energy state, they re-emit a photon. So we send in photons, causing them to flip to the high energy state, and then they re-emit. And to be clear, when they re-emit, when this one re-emits, it could send out the photon in any direction, not just to the right. They've simplified this for reasons that will become clear on the next slide. The idea is this could be sent out in any direction. Is everybody okay that when it re-emits the photon, it doesn't have to go the same way that it came in? Is everybody okay with that? All right. All right. So far, so good. All right. Let's go over to here. Take a human being, shove them in a solenoid. That's what we got right here. Oh, there's too many drawings. Do you agree? Okay, inside of that human being are molecules. Inside those molecules are nuclei. Those nuclei have spins. The spinning nuclei have, they're not really spinning like billiard balls, but they have magnetic moments. Great. Right now, there's an external magnetic field. Okay, that's cool. What I might do is I might change the external magnetic field so that there's a gradient. Okay, now I want to be clear. Do you see these little arrows right here and right here? Those are representing the external magnetic field. I want you to watch what happens to those arrows as I jack up the gradient. You see some of them are bigger and smaller, right? There's a gradient. There's a change from left to right. We could make a gradient vertically. Do you agree we could be able to do this with some coils, right? Maybe some Helmholtz coils that could change the field a certain way, right? And so now think about this. What have we done? Each different nuclei has a different magnetic field. Each different nuclei should respond to a different radio frequency. Agreed? We could send in a lot of different radio frequencies simultaneously, and we know that each different position in the body corresponds to a different radio station. You can send in radio signals, and whenever it spits it out, you can tell where, okay, so basically now if I jack up this power, let's send in some photons. Most of them are not reacting. Do you agree? So maybe I could change the frequency. Let's try this one. There, do you see that some of them are reacting now? And the idea is you put a detector over here on this side that I'm going to circle as soon as I can get this. Oh, where's my marker? There's a detector over here. And the idea is if your detector can discriminate between the different frequencies by doing a fast Fourier transform, perhaps, we could describe how many nuclei are in each location. So if somewhere has a tumor with a bunch of extra nuclei going berserkers, we could detect that tumor. You know what I'm saying? Isn't that wild? So this is nuclear magnetic resonance, which nobody liked that term because it had nuclear in it, so they changed it to magnetic resonance imaging. Pretty cool, right? Oh, geez, it's time to go. I told you I'd be late. That was it. So this is sort of interesting. Obviously, I'm not going to have this question on the test and say explain MRI, but I thought I sent you some videos if you want to see this in detail. I think it's kind of cool. This is where I wanted to go with that mu dot B crap. Got it? And I should be careful. It's negative mu dot B. All right. We're done. Next time we do EM waves, I'll see you Monday after Thanksgiving. There's a pre-lab due tomorrow. Pre-lab due tomorrow. Pre-lab due tomorrow. I sent you all the crap yesterday. Just find the Canvas announcement. What do you do on Sunday night after Thanksgiving if you have questions?
Go talk to Youngblood.
Talk to Youngblood. Where do you find that information?
It's on campus.
Somewhere in Canvas. I'll try and send it to you again, but I already sent it. So his Zoom link is there, the time's there, everything's there. Okay. Yes, Jacob, I just saw your text about the truckload of transistors. Yes, absolutely. Sorry it took me so long to see that. All right, any questions from Zoom? I'll see you all
I have
later.
an unrelated question.
All right.